So x2 will be that z2 with probability exponential, or I wrote e, why exponential, e to the power beta I have fz2 bigger than fz1, so it is fz1 minus fz2. Is that a valid probability? You have to think about this condition. I got a z2 that turns out to be bigger than z1. So ideally I should not take that. Okay, so intuitively I should not take that. I am saying that don't discard it. Allow it some chance. Why am I saying this? Because this is your way to escape from possibly getting trapped into a local minimum. Okay, so with this probability, you take x2 to be z2, though z2 is inferior to z1, and equal to z1, the original one. That means you retain the original one with probability 1 minus that thing. Now let's examine these expressions carefully, what is happening here, so that we have an understanding of what we are doing here. See, if fz2 is much bigger than fz1, then z1 is a very bad choice, right? In that case, what will happen to this probability? This probability will also be very small, right? Because it's exponential of this thing. I'm not specifying the constant beta yet. That will come later. So this will be a small probability in that case. So in that case, this procedure will let you choose z2 over z1 with a very small probability. On the other hand, if fz2 is larger but not by much, then they will be close, and then you choose them with a higher probability. Now this is something I can do very easily, right? All I need is to ensure that I can generate an outcome with this probability. That's all. So like that I construct my x2. So here comes my x2 and that comes there. So x2 may be z1 if x2 may be equal to z2, the new one. Okay. So the idea is whatever I get as my new thing, if that is already superior, I keep that. But if it is not superior, I still give it a chance. This might get discarded as the chain proceeds. So like that, I create my z3, z4, zn, and I go on creating my x's. Like that. So this is the magic formula. What happens is that if you do that, do you realize that you are generating a Markov chain? Because at each stage, if I look at x4, its conditional distribution given x1, x2, x3 depends only on x3. Right? That's obvious, the way I have generated it. So this is a Markov chain. It's a finite state space Markov chain. And if I follow the steps that I am describing here, it is clear that I can move from any point to another point with positive probability. That's also clear. So it's an irreducible chain. And also you can show that it will be aperiodic. That's not a problem. Okay? So in fact, the way it has been created, you can show that the transition probability matrix will have all its entries positive. Okay. So only thing that remains to be shown is that Gibbs distribution turns out to be the stationary initial distribution for this chain. So that's the achievement in the whole exercise. Okay. Now that requires some algebraic verification, very routine algebraic verification. I have described the chain, how it is generated. You have to write down its transition probability matrix and check by direct algebra that this is the stationary initial distribution. That means you have to take this distribution, multiply, and there is a very standard multiplication, and you will see that it is an invariant distribution. So the beauty of this result is that I am generating in the limit from this distribution without evaluating this partition function. So that's the strength of Markov chain Monte Carlo. But you are not getting it in a finite number of steps. So it's a limiting result. So if I run this chain long enough, in the limit, I will achieve this distribution. So for any fixed beta, you can prove that the Markov chain that we have generated will have this Gibbs distribution as the invariant distribution. Okay. This is the famous Metropolis-Hastings algorithm. The algorithm that I have just described is nothing but the Metropolis-Hastings algorithm. So Metropolis and Hastings did that sort of independently. Hastings did it in a more general. So the description that I am giving is really due to Hastings. Okay, Hastings is, the paper of Hastings appeared in Biometrica. Metropolis had this paper with few other authors. That appeared in a journal called Journal of Chemical Physics. Okay, so they were thinking about thermodynamics problem and such things. So that's why they published there. So this is the Metropolis-Hastings algorithm. So what is finally the result? The result is so you see that this step, this is what prevents you from getting trapped in a local minima.
What is the role of beta?
Larger the beta, my distribution has higher chance of selecting the minima. That's the role of beta. But I am doing it for a fixed beta as of now. Okay? So the limiting distribution that I will be creating by this procedure is not going to give me that uniform distribution only on the set of minima, but close to that probably. If I do this for a large enough beta, it will give me that. But ideally, what should I do now? I should, as this chain proceeds, I should change beta also, right? And then my transition probability matrix changes, right? Because then the creation of xn is not done using the same transition probability matrix as the creation of xn, -1. So now you see why I was talking about inhomogeneous Markov chains. So in order to solve the minimization problem, you have to create really an inhomogeneous Markov chain. And that's why all these results that I mentioned about contraction coefficients and their behavior for product matrices, they will come. Okay. So, yes?
So which probability is called beta? Fz1 minus Fz2.
Yes.
So but Fz1 is greater than Fz2.
No, no, no. This is in this case.
In this case, X2 equal to Z2?
Yeah. So with that probability, I will take Z2. So it's like Z2 is inferior to Z1, but I still take that with some probability.
Fz2 is greater than Fz1.
Yes. So because it's a minimization problem, I should not take Z2. But I am doing that with a small probability so that I don't get trapped in a local minima. Okay. And what is the final outcome? If I follow this algorithm, I end up getting a Markov chain for which the limiting distribution is the Gibbs distribution.